Yeah. So I just want to gauge like a general background that the audience has so that I know where to slow down and where to speed things up. So I hope everyone knows how tensor products work, right? Uh, so like main thing that are important are tensor products and the definition of algebra, which I'll go over once. So if you know some linear algebra, if you know what vector spaces are, you're good. And even if you don't understand the theory behind tensor products, that is fine. We will need only a functional understanding of it. All right. So um, so I think I'll first start by talking about what are quantum groups. So that's kind of a difficult thing to answer without first building up a lot of mathematical machinery, right? So what are quantum groups? So this is just a quantum groups is just another term for what we call quasi-triangular Hopf algebras. So quasi-triangular Hopf algebras are a specific type of Hopf algebras. And so what do all of these words mean? Will that's kind of what this talk is about. We'll build up to that. Um, so why study quantum groups is kind of the question, and the when you see the definition, it's going to seem very abstract. So how do you come up with the definition in the first place? So one of the motivations is that in classical physics, the space time that we have, the Lie bracket that we have, it commutes, right? So that's not the case when you consider, say quantum geometry, where things are non-commutative. The space time itself is non-commutative. Even in relativity, that happens. So when you are faced with non-commutative geometry, you kind of need something to represent the role of groups, to capture the symmetries of the space-time. And that is kind of where Hopf algebras come in. They kind of do that. And but I don't want to get too much in the details of the motivation of Hopf algebras, because these and quantum groups, because these objects first popped up in things like quantum integrable systems. And today they have a lot of applications in a variety of things, from pure mathematics to mathematical physics, things like knots invariants, for example, knot theory, and non-commutative geometry. Then on the mathematical physics side, these are also important in things like quantum gravity and stuff like that, right? So So yeah, the point being that these are objects of importance in a lot of subfields, and that is kind of the motivation for studying them. Right. So what I'm going to do is I'm just going to start off with discussing what the definitions are, and before we discuss the definition, we need to build up some tools, right? So I'd like to start off by reminding everyone something pretty basic. So what is a vector space over a field, right? So we have this particular uh, quadruple, right? And we so the things that we require is that vn plus, they form an abelian group, right? And additionally, there is a there is an action of f on v, right? And this is a group action, right? And this group action is what we call scalar multiplication. And again, the usual properties hold, and because we are defining this as a group action, the some things like, for example, lambda mu v would be equal to lambda mu times v. So all the desirable properties hold, right? And then of course we require the distributive law to be satisfied, right? So v plus u is equal to lambda v plus lambda u, and of course this distributive law is commutative, so it holds the other way around as well. right? So this is what we have in a vector space. Now, uh, one thing to notice here is that what we are working with so far, the main operation here is the addition of the vector, is the addition in the case of vector spaces, right? So what happens if we introduce, say, another operation? So let's call it the multiplication, which is not really the scalar multiplication, because remember, scalar multiplication is a map that goes from that is a group action of the field on the vector space. But what I want to do is I want to introduce a multiplication operation inside the vector space. So in this case, what I have is that the vector space is closed under the addition operation, but I would like to give it another group structure by introducing the multiplication operation. So to not confusing it with scalar multiplication, I'm just going to denote it as M. All right. And if we do that, we end up with a new structure, which we call an algebra. So more specifically, I'll denote it as mu actually. That would be a little simpler. I'll denote it as mu. So, right. So what I have is the notion of an associative unital algebra. All right. So what do all these prefixes mean? So associative means that, well, the associative condition holds, the multiplication is associative, and unital means that there is a multiplicative identity in the set V. Right, so if you're familiar with rings, you know that we often have like what we require in the ring is that r plus is an abelian group, but r and the multiplication, it need not be an abelian group. We just require it to be uh, a semi group, right? In fact, we don't even require that the multiplicative identity belongs to this. So if multiplicative identity does belong to r, then we call it a unital ring, and if multiplication is commutative, then we call it an abelian ring, and so on. Right. So it is a similar kind of thing here. Right. So let me state out let me state out formally what these axioms are. All right. So firstly is that we call A an algebra. All right. So let's say that my underlying field is K. Then I'll call. Let's suppose this is my vector space. All right. And this is equipped with another product. Equipped with a product which I'll call mu, such that mu is a bilinear map. All right. So it goes from A cross A to A. In other words, what I mean is that let's say that I am applying mu on A comma B, then for A and B in the vector space, then this could be anything depending on how we define multiplication. But when I say this is linear in both of the arguments, I mean that uh, a condition like this, for example, this would be given by lambda times mu of A comma B plus mu of A prime comma B. All right. And similar linearity would hold in the other argument as well. So that's what we mean when we say that mu is bilinear, right? This is a bilinear map. All right. And then additionally, because this is a unital algebra, we also require that it has a unit map, and we call the unit map this. So it goes by this. It goes from the field to the vector space, right? And both of these maps satisfy two axioms. All right. So first is the axiom of associativity. Right. So what does this axiom say? This says that if I were to compose mu, the multiplication map, with identity tensor product with mu, that equals mu tensor product, mu composition with mu tensor product identity. So again, we already have tensor products popping up. And why do we have that? I'll discuss that in a minute. And the second axiom is the unit axiom, right? And what is this axiom? This just says that the composition of mu with the unit map uh, tensor identity is equal to identity, which is equal to mu composition of identity tensor the unit map. Okay. So what does all of this mean? So let's slowly unpack that, right? So okay, so let's think about what associativity means in the first place, right? So if I have this product ABC, then that should equal A times BC, right? This is what we mean by associativity. But now the thing is that um, I can't just write it as composition here. The reason being that the map, the multiplication map is bilinear, right? So there is a very nice way in which we can encode bilinearity by a linear map, and some of you may know where I'm going with this, which is the universal property of tensor products. Sorry, the universal property of bilinear mappings, right? So what is this? So in general, imagine that you have two vector spaces, let's say E cross F, right? And you have a bilinear mapping phi that goes from E cross F to another vector space. I'll call it H. Then what we have is that there is another bilinear map, which we call the tensor product, that maps it to another space, which we denote like this, but we could also denote it by something like say T, but we denote it as a tensor product, such that from this space to the space H, there is a linear map F, right? So one way to think about it is that if I have a bilinear mapping, I can break down the bilinear mapping as into a different mapping, right? This is, I can factor the bilinear mapping as the uh, tensor product along with phi, along with F, right? Sorry, this should be the other way around. Yeah, like this, right? So why is this important? Because it gives me a nice way, the tensor product gives me a very nice way to encode bilinearity of a map using linear maps. So when I'm saying that phi of A comma B is bilinear, all I need to say is that phi of A tensor B is linear. F of A tensor B is linear. So I have this nice way of reducing bilinearity to linearity of a different map, right? So that is what we are using here in both of these axioms. That is why we see the tensor product. All right. So now, of course, there are a couple of questions here, such as how do we know that such a map always exists, such a linear map F always exists, and such a tensor product always exists? Well, I'm not going to prove that here. We're just going to take this universal property on faith, and we'll just roll with it. All right. So now, uh, so for our purposes, all I want to think of tensor products is some operation that we can do on vector spaces. Right. And it's not just vector spaces. We can do it with algebras as well, and other some other structures as well. But for now, we'll focus on tensor products of vector spaces. And of course, here we are taking tensor products of mappings. That's also very much possible. So in general, what I want you to think of is that the tensor product of two vector spaces is just the cross product modulo some relations. So when I say modulo certain relations, I mean that whenever these relations are satisfied, you bundle them into a particular set, and it would be isomorphic to those equivalence classes, right? So what are the modulo relations? Well, firstly, it is, well, all the relations of bilinearity that you would expect. So we have that lambda v comma w is equal to v comma lambda w, and then v plus x comma w is equal to v comma w plus x comma w, and so on. Like all these standard relations that you would expect for bilinearity to hold, and these spaces would be isomorphic. So a tensor space is just the cross product modulo certain relations. All right. And so in a lot of ways, it is similar to the cross product linear space, to the E cross F linear E cross F vector space. All right. But this has some extra special properties as I've discussed. All right. So now let's think about what these axioms are exactly saying. All right. So I will just so what I'm going to do is that I'm going to draw these axioms in terms of commutative diagrams, right? So let's start off by thinking about what associativity means in terms of the maps, right? So imagine so what I have is a set A, right? And I'll consider the space A, tensor A. Again, I'm considering the tensor product because I'm dealing with bilinear maps here. So this way I can just enforce it by choosing a linear map that goes from this to some other space, right? So when I say this is associative, what I mean is that first I can take the tensor product of these spaces and then of the other space, and that is going to be the same as taking the tensor product of the second and the third space first, right? So what I'm doing here is that first I will multiply them together while keeping this fixed, right? So here I get this part, and then I will multiply all this thing together, right? So in terms of a more concrete example would be something like, let's say I have this particular situation, right? So what I'm doing is that first I'll multiply these two, so I'll get AB multiplied by C, right? So I'm applying the multiplication map here, and I'm keeping this fixed, and then I will multiply these two together. So I will end up getting, then I'll multiply mu on this, so I'll end up getting ABC, right? So this is how we are. This is what we mean when we say that we are uh, when we apply associativity, right? The order in which you take the product doesn't really matter as long as the order of the symbols is the same. So I can't write this as ACB, but this is not true. But it doesn't matter if I multiply these two first or if I multiply these two first, right? So I get this part. But what is this part saying? This is saying that, okay, first you keep this A fixed. So you'll end up with the identity, and then you multiply these two. So I'll get the multiplication map here. And then I will apply the multiplication on all of this. So I end up with this. And if you notice, this is exactly what the first axiom says, right? The associativity. So I can actually express this in terms of commutative diagram like this. So I start off with A, tensor A. And again, like I discussed, first I want to consider what happens when I group both of the first two spaces together. In that case, I am taking mu tensor identity, right? And I'll end up with a space that is A cross A. But then I could apply the multiplication map again, and I'll just end up in A, right? Now I can do the same thing here, except that this time I'll reverse the roles of identity and mu. So this would be interpreted as multiplying the second and the third term first and keeping the first term fixed. I'll again end up with A tensor A, right? And then I can apply the multiplication map again, and I'll end up in the space A, right? So this is my commutative diagram for the associativity condition. Now, what is the unit condition? Well, the unit condition is saying that well, if I start off with the vector space K tensor A, right? And now what I'm going to do is that I'm going to apply the identity map. Sorry, I'm going to apply the unit map and then identity map. All right. And if I do that, I would end up with a vector in this space. Why? So what does this tensor product mean? So it means that first, the way tensor products distribute. So when I write, say, F tensor G acts on A tensor B, what I mean is that F acts on A. So F and G are functions here, and A and B are arguments. F acts on A, uh, which is then multiplied by G acting on B. All right. So if you think about it, we know the unit map, the way we defined it, it goes from the field to the space A. So this K, the unit map would act on the K, and the K would become this A. And the identity map is just going from A to A, right? So it keeps the A fixed. But I can also have this the other way around, right? I can also have this the other way around because this is the same as, say, having A tensor K. So this is in the opposite orientation, right? And this time I will apply identity tensor I, right? So I'm keeping the A fixed and I'm applying the unit map on this, on the K, right? And I think everyone knows that these fields, these products are isomorphic to the space itself, right? I think everyone knows that. So I won't be proving this, but these are the trivial isomorphisms. And then I can apply the product map here to get to this part, right? So when I say that my when I say that the identity, sorry, the unit axiom holds, all I mean is that this diagram should be commutative. It doesn't matter which way I travel the diagram, right? So this diagram is commutative, and that is exactly what is spelled out in this axiom over here, the unit axiom. All right. So just to recap, we have these two commutative diagrams over here. All right. And whenever these two diagrams commute, we say that the space A is an algebra over the field K. All right. Is this clear? Do you guys have any questions?
One thing in the definition of bilinearity relations, I guess the scalar rule is different. Written wrong.
Could you repeat? I couldn't hear you clearly.
Um, I'm not sure if you can see my mark. So here it should be lambda times v comma w, right?
Where?
Here uh
Lambda times A.
lambda v comma w. Yeah, where where Shreyas cursor is there.
Okay, so you're talking about this part, right? Where we discussed
Okay. Yes,
the
yes.
okay. So so what we are saying here is that certain if you just consider the space E cross F, right? Then in this space, I'm sorry. Yeah. So if you consider just the space E cross F, right, with no additional relations, in this space, the terms lambda v comma w would not be equal to v comma lambda w. All right. But in tensor product space, what we want is for it to have the property that lambda v tensor w is equal to v tensor lambda w. So we say that we will just group these together and they would belong to the same equivalence class.
Got it.
Yeah, so that's why I'm saying that E tensor F is isomorphic to E cross F modulo some further relations where we would group the properties that we want to be together. Right. So in I'll just quickly talk about the properties of tensor products that are relevant here. So for example, when I have a lambda v tensor w that is equal to v tensor lambda w. And similarly, bilinearity also holds. So v plus w tensor x is equal to v tensor x plus w tensor x. So it is distributive over addition. And these are the some properties that we like tensor products to have. All right. So I hope this makes sense.
Yeah.
And this also holds in the both the arguments. So v tensor x plus y would also be v tensor x plus v tensor y. But in general, it's not necessary that v tensor x is equal to x tensor v. This does not hold in general. So there's only some relations that we that are present. Commutativity is not one of them. Right. So all I'm saying is that if you identify this with the pair lambda v comma w, then in the tensor space, I want that pair to be equal to the pair v comma lambda w. So that's why I'm introducing this. I'm using the terminology modulo this relation. So to mean that I would regard them as being equal. So one analogy that you can think of is that when you consider the space, say Z cross Z modulo PZ, in this space you regard say P plus 1 as being congruent to 1, right? Because they are essentially the same, because they leave the same remainder divided by P. So that is exactly what we mean here, except that relations are somewhat different. So you would say that P plus 1 and 1 belong to the same equivalence class. That's the same thing here, except that it's just different relations. That's it. Okay. I hope it's clearer now. So having discussed algebras, uh, another thing I'd like to introduce is the concept of co-algebras. Right. And before introducing this, I want to make a couple of remarks. All right. So duality is pretty it's like a central concept in maths, right? We have a lot of objects that are dual to each other. So when we talk about duality, what we mean is that they are very um, a crude way to describe it would be that they're very intimately related. So whenever a particular statement holds for this object, an analogous statement would hold for this object as well. And when that happens, we say that these objects are dual. So an example would be that if any of you have studied projective geometry, any theorem that contains the terms points and lines, right? So I might have some theorem that looks like this. And then if you just swap both of these terms, the theorem still holds true. And this is the duality that we see in projective geometry, right? And some other familiar examples of duality would be, say, in topology. So open sets and closed sets are dual to each other, in the sense that when we say that all union of union of open sets is open, that is the same as saying that intersection of closed sets is closed, right? So there is a certain correspondence between all the statements that you can make about open sets and all the statements that you can make about closed sets. So this is what we mean by the principle of duality, right? And the interesting thing is that, again, remember that A is also a vector space here, right? So I can consider the dual space of the space A, right? And it is possible to give this dual space a structure that resembles algebras, but it's not quite algebras. Instead, this structure is what we call co-algebra. All right. And so what is this structure given by? Well, uh, co-algebras, you get them by just reversing all the arrows in both of these commutative diagrams. All right. So remember that in an algebra, what we had was a vector space A along with a product map, which I'll call mu, uh, right? And along with an identity map, right? A unit map. So I'm going to denote an algebra like this for brevity. All right. So what I can do is that I can consider another corresponding set, which I'll call so on the dual space A star, along with another product map, except that this is not quite a product map. We call it the co-product, and another unit map, except that this is not a quite the unit map. This we call the co-unit. All right. And this structure is what we call a co-algebra. I'll give the formal definition in a minute. So this structure is what we call the co-algebra. And this structure over here is what we have in algebra. And these objects are dual in the sense that on any algebra, you can give the dual space a co-algebra structure. All right. And I'm sure that, as you all know, in linear algebra, that the dual of a dual space is just isomorphic to the space itself, right? So it's no surprise that when you consider the co-algebra structure, you can take its dual space and give it an algebra structure. So, in this sense, the theories of algebras and co-algebras are dual to each other. Because every theorem you have about an algebra, you can find a corresponding theorem about co-algebras. And for the discussion to follow, it will be beneficial to have a structure that is comprised of both an algebra and a co-algebra. All right. So, what is specifically a co-algebra? So, let me take you back to the associativity axioms, right? So, associativity axiom looks something like this, right? We had uh, we had this condition, one way associativity, and then another way. So this would be identity cross mu, and then again mu, right? Now, what I'm going to do is that I'm going to reverse all of these arrows and change the labels a little bit. All right. So instead, I'm going to have an arrow that goes like this. So all the uh, all the arrows are reversed. All right. So now I can no longer have a map mu, right? Because remember, mu goes from A tensor A to A, right? But here I have a map that going from A to A tensor A. So I'll call this my product map, except that it's not quite a product map, so I call it a co-product, right? So this is the co-product map. Similarly, before what we had was the unit map, right? That went from the field K to the vector space A. But now I'm going to have a co-unit map that goes from A to K, right? This is called the co-unit map. So what I'm going to do is that I'm going to change the labels accordingly so that I end up with something that I would like, uh, right? So this time I'll call it delta because that's how I'm denoting my co-product. So I'm going from A to A cross A, and then again I'm going from that to this, right? So here yeah, here you'll see that this A stays fixed and gives me this A, and this co-product map takes this A and turns it into A cross A, because that is my definition of the co-product, right? It goes from A to A cross A, and it will do the same thing here, here above, right? So what we have now is a condition that is not quite associativity, but it is a dual to associativity, isn't it? So I'll call this condition co-associativity. All right. And I would have a similar process with the unit axiom, right? So what we had in unit axiom was this, right? So I'm just going to write down the unit axiom first. So what we had was this being identity times iota, and over here it was iota times identity, and then these were isomorphic to A, and over here we had the product map, right? And the unit axiom was that this commutative diagram commutes. But now, again, I'm going to do the same thing that I did before. I'm going to reverse all of these arrows. All right. Actually, I don't need to reverse the isomorphism arrows. It doesn't really matter, right? Isomorphism will still hold. So I just need to reverse these arrows, right? So now I also need to relabel these things. So instead of iota, I would now end up having eta, because that is my co-unit map as is defined here. So you see that this A is being mapped to this K, and this A is staying fixed, right? Because that's the identity map there. And same thing is happening here. This A is going to this field. And this time I'll have the co-product map here, right? So this is what we call the co-unit axiom, because again it is dual to the unit axiom, right? So, in other words, what I have is that a structure C delta and eta is called a coalgebra if the above diagrams commute, right? So if I want to write the above diagrams in a more symbolic manner in terms of a particular formula, I can do that pretty easily. So what we would end up having is that let's try to derive it from the diagram, right? So first we take delta, right? Let's look at the co-associativity axiom. What we are doing is that first we take delta, right? And then to that delta, we apply identity cross delta, right? And then because the diagram is commutative, the above way of going should also be the same. So we have the equality. And now this time we are first again applying delta, but we are composing it with delta cross identity, right? So we get from this diagram, we have now written down our co-associativity condition, which I'll label as C1. We can do similarly for C2, right? What this is saying is that we go from first we start off from A, then we go to A cross A. So again, we are starting off with delta, and then we are going to we are applying eta cross identity, right? And notice that this is the same as this isomorphism, and so it would be yeah, this is the same as this isomorphism, so it would just be equal to the identity map itself, right? And similarly, this side would also commute, so I will write that down as well. So again, we are first applying delta, and then to that we apply identity tensor eta, right? So this is what the co-unit axiom and the co-associativity axiom tell us. And whenever these two axioms are satisfied, we call the resulting structure a co-algebra, right? So now what we have developed so far is an algebra structure and its corresponding dual structure, right? So now, before we move on further, I also want to introduce a particular notation. All right. So, in general, when I think about the co-product, all right, I am taking the co-product map and it's going from the space C to C tensor C, right? C is my co-algebra. So what is the general element in this going to look like? Well, any arbitrary element is going to look like, say, Ci tensor Cj, but it's also closed under summation, isn't it? So I will just add a sum here. So a random element is going to look like this. So I can say that delta of C is going to look like this. The problem is that this can be a little bit cumbersome to write. And often what we care about is not what these elements are in particular, but the structure of the tensor product. So what do I mean by the structure of the tensor product? It's that when I'm thinking about how different operators, how different functions act on a tensor space, I'm only concerned with the order in which this product appears, right? I don't care if it is Cj tensor Ci instead. I only care what is the what is the first element, right? So what we do is that we denote it like this: C1 in brackets tensor C2 and a sum over this. So what does this mean? It means that the term C is mapped to so summation is over I and the summation is finite. So all we mean is that the element C is mapped to another element that has this form, where there is a summation of tensor products, and and we don't really care. These C1 and C2 are not really variables. They are saying that C1 just means that this is the first term in the tensor product, and C2 just means this is the second term in the tensor product. So this notation is what we call Sweedler notation. And this is really important because it's going to simplify calculations a lot. All right. And it is also possible to phrase all the axioms in this notation, and they look very simple when you do that. All right. So now a couple of things to be mentioned about Sweedler notation, and I think they're best understood through some examples. Right. So again, the thing I know I'm repeating myself, but what I really want to reiterate is that C1 and C2 are not variables. They are representatives of what the structure of the tensor product is like, right? So C1 just means the first term in the tensor product. C2 just means the second term. So let's look at the co-associativity condition, for example. All right. So why do I want to look at this? Because it's a nice example of how Sweedler notation behaves, right? Let's take a look at the associativity condition. So I have tensor A, right? What is a general element in this space going to look like? Well, a general element would look something like this, right? We would have a sum of 1, 2, sorry, of the first product, then the second term, and then the third term, right? This is what a general product is going to look like. But the thing is that, let's say that S is equal to A cross A, right? Then can't I also write this as S tensor A? I can, right? And a general product in this space is going to look like C1 tensor C2. Again, the C1 and C2 just mean the order in which the tensor product acts, right? But now notice that there is nothing wrong in saying that. All right. Note like if I'm considering this above notation, what I would have is that C3 would be the same as C2 when C1 tensor C2 would be the same as C1. But again, I am interested in what the structure of the tensor product looks like. But now the thing is that I can also write an element in S, right? And general element in S as C1 tensor C2, right? A sum of this. So I'm going to rewrite this also as the sum of C11. So this 1 means that it is the first. So this one means that it is the first term in the tensor product in the term C1 multiplied by C12. So this 2 is telling me this is the second term in the C1 term multiplied by C2. So this is a perfectly normal way. This is a perfectly acceptable way to write what I've written here. And now I can do the same thing, but this time the other way around. Because S is A cross A, I can also consider this space as being A tensor S, right? A general product in this one is going to again look like C1 tensor C2, which I can rewrite as, well, C1, but this time I will have these 1 and 2 subscripts following this one. So this would be C21 tensor C22. Right? So these 1 and 2 are again just telling me what order the C2 tensor product is appearing in. So what is the purpose of mentioning all of this? Well, I can now rewrite the associativity axiom as like this, right? That the sum of C1 tensor C2 tensor C3 can be written equivalently as the sum of, well, C11 tensor C12 tensor C2, which can be written equivalently as C1 tensor C21 tensor C22. All right. So I hope this example makes it clear that these subscripts that we write in round brackets are just representative of what the tensor product structure looks like. It is not a variable itself. So if I want to understand how operators act on tensor products, this is going to be very useful. All right. And also, a lot of the times, you will see authors omit the summation sign altogether. And this is especially common with physics people because it's like a, so in Einstein's summation convention, when you have repeated indices, so if I have a sum that looks something like, say, AI j multiplied by say bki, the summation over I is kind of implied. That is the Einstein summation convention. All right. And so often you will see this written without the summation being implied. So sometimes authors do that with the summation Sweedler notation as well. All right. I won't be doing that because I don't want to make things more complicated than they already are. But that is often done. So now let's take a look at how some other things would behave in this Sweedler notation, right? And a lot of axioms would take a particularly simple form. So I want to take a look at what this the co-unit axiom would look like, right? So now again, a reminder of how two different functions act on a variable in the tensor space. So how does this work? That is going to be f will apply on the first argument. You'll take tensor and sorry, you will take product, and g would apply on the second argument. All right. So I'm going to now show that in this context. So now, what is a general element in delta going to look like? Well, whenever delta maps a C to something, it is going to be a sum of C1 tensor C2, right? So when eta and identity act on it, again, these are linear maps. So what I would get is that when I apply this axiom on when I apply this on a particular term C, I'll first apply delta, which would look like eta tensor identity being applied on delta of C, right? So that would be applied on eta tensor identity on on the sum of C1 tensor C2. So I will apply eta on the first part. So I would get sum eta of C1, and then it would just be the product with identity, which would just be C2. So I hope this makes it clear why the Sweedler notation is so important, because all this is telling us is that the eta should act on the first part and keep the second part fixed, right? And I can rewrite rest of the part in the same way. And since the this is equal to identity, I can say that yeah, I can say that this is the same as C, and from this side, I would just switch the positions of eta and identity, so which would be the same as the sum of C1, but this time eta of C2, right? So this is telling me that the order in which eta acts is really irrelevant, and all of this is just going to equal the identity map. So this is an example of how we work with the Sweedler notation. I hope this is clear. So yeah, do you guys have any questions before we move on to the next thing? Okay. So now I think this is a good time to kind of give some examples. So I'll do that now. All right. So there is this one example that is quite simple, and we'll be using that example throughout the rest of this talk. All right. So what is this example going to be? This is the group algebra. All right. So what is the group algebra? Well, a group algebra, which we denote as KG, right, or K capital G, I'll denote a group with the capital G. So here, G is a group and K is a field. All right. And an element of the space is of the form AI times GI. All right. So I'll call this GI. All right. So here, AGI is member of the field. This part belongs to the field, and this part belongs to the group. And the sum is finite. All right. This just goes over all any number of elements that you want from the group, but it has to be finite sum. All right. So in other words, this is what a general element of this space is going to look like. Okay. And the operations are defined in the simple way. So if I have, say, something that looks like alpha I g plus the sum of beta I h, that is just equal to the sum of alpha I plus beta I times g plus h. All right. So the coefficients add, and so does the yeah, the coefficients essentially add. No, sorry. Wait. I'm sorry. This should be g here. Yeah. So yeah, this is what it would look like. And when you're multiplying two terms, what does that look like? Well, let's say I have again alpha ig multiplied by the sum of beta ig, beta I. Yeah, let's say it's g. Then and of course the sum is running over g. Okay, and it's a finite sum. All right, the sum runs over g, and the sum is supposed to be finite. So what does this look like? Well, this sum again runs over g, and it's finite sum, by the way, such that I'll denote this by h here. So what is going to happen when you multiply two things, right? Let's think about it. What is going to happen? Well, let's say I have one term that looks like, say, alpha 1 g1 plus alpha 2 g2, and I multiply that with h1 g1 plus h2, let's say g3. What is beta 1 g1 and beta 2 g3? What is that going to look like? Well, you would just multiply it out and you would end up with something that looks like this, right? G1 squared plus alpha 1 beta 2 G1 G3 plus alpha 2 beta 1 G2 G1 plus alpha 2 beta 2 G2 G3. And since we are working over this group, this these products, right? There are going to be some other elements in the group. So what I'm going to end up with is just the sum, such that, well, first of all, I need to collect all the terms that are the same, right? So let's say that G1 and this terms are the same because both of these are equal to, say, some h, then the coefficients would add up. So I would have xy is equal to h, and this again, x and y again belong to g. So then I would have alpha x and beta y multiplied by the h, right? So this just means that I'm collecting the like terms and I'm summing over all possible terms that this product would give me. All right. So so this is what my algebra structure is going to have, and it is pretty easy to check that this has an algebra structure under these addition and multiplication. All right. But now what I want to do is see what the co-algebra structure on this is going to look like. All right. So what I'm going to do is I'm going to define the co-product to be just G tensor itself, and the co-unit map to be just the identity map. Sorry, co-unit map just maps at everything to one. All right. So let's verify the co-associativity axiom. Right. Again, what does the axiom say? That delta cross identity of delta is going to be equal to identity tensor delta of delta. Right. So let's work out the LHS first. LHS has applied to, say, some element G. What is that going to be? That is going to be delta tensor identity applied to delta of G, which is going to be delta tensor identity applied to G tensor G, which is just going to be delta of G tensor G, because identity of G is just G, which is going to give me G tensor G tensor G. And I'm not bothering writing brackets because tensor product is associative. All right. And you can do the similar thing on the right hand side and you will end up with the same thing. So co-associativity axiom is indeed verified. We can now do the same thing for the co-unit axiom. What is the co-unit axiom? Eta cross identity as applied to delta is equal to identity, and it is equal to identity cross eta as applied to delta. Right. So let's check this. So I'm going to be applying this to delta of G. What is that going to give me? That is just going to give me, well, uh, eta tensor identity as applied to G tensor G, right? And that is going to give me, again, eta times G tensor G. That is going to be what? Eta just sends everything to 1. That's going to be 1. And identity times G is just G. So that just gives me the thing that I want. And you can again check this on the same thing, but with the other one, with the other side, and that again gives you the same thing, right? So it does give me the identity map, and so will this one. So will this part, right? So what I've verified now is that when I give group algebra this structure of co-algebra, it does make it a co-algebra when the co-product and the co-unit maps are this, right? And again, the multiplication and the standard multiplication and the unit maps are as what they're obviously. All right. And now we are going to see that as we move throughout this talk, this is actually going to be turned into what we are going to call a Hopf algebra. All right. So I think one thing is clear from this example, that this group algebra has both the properties, right? It is both an algebra and it's a co-algebra, isn't it? So what I'd like to do is that I'd like to introduce a new notation, a new definition. All right. And I'm going to define what I'm going to call a bi-algebra. Right? So what is a bi-algebra? Well, the definition is quite obvious. It is just going to be an algebra it's just going to be a space that is both an algebra and a co-algebra. So more formally, let's call it by H. Uh, so I'll have H plus the standard multiplication, which I'll call mu. Then I would have the identity map. I would have the co-product map and the co-unit map. All of this over the field K. So this is going to be my bi-algebra structure if, first of all, H plus and K form a vector space. All right. And additionally, H mu is algebra over K, H mu and identity, unit map, and H co-product and the co-unit map is co-algebra. But now the problem here is that I don't have any way to relate both of these structures, right? So I'm going to do that now. And the way I'm going to do that is by this. I'm going to define it in terms of homomorphisms of algebras. All right. In particular, I'm going to require that delta is an algebra homomorphism. So it gives me this. I'm going to require that similarly delta of 1 is just 1 tensor 1. Then I'm also going to require that the co-unit map is also an algebra homomorphism. And the co-unit map of 1 is just going to give me 1. So in other words, what I'm saying is that delta and the co-unit map, the co-product and the co-unit maps are algebra homomorphism. Now, interestingly, so like I had mentioned before, algebras and co-algebras are dual to each other. So any statement that I make about algebras or co-algebras has a corresponding statement in the other domain, in the other set, right? For the other structure. So if I require that delta and eta are algebra homomorphisms, I automatically have that the multiplication map and the unit map are co-algebra homomorphisms. All right. So one actually implies the other. And in fact, it goes the other way around as well. So I could have used either of them as a defining property to say that, they are define the compatibility of algebra and co-algebra. Right. But we usually define it in terms of delta and eta being algebra homomorphisms. But of course, defining it either way is really equivalent. And how do you see that both of these conditions are equivalent? It just follows from the commutative diagrams that we saw before. All right. So one more thing that I want to discuss is why are these like again another example of how Sweedler notation behaves, right? So in particular, I want to focus on this part. How would we write this in Sweedler notation? So I'd like to solve a reminder, which is that when I have the product of tensor product, what does that look like? Well, this is just equal to h prime tensor g prime. All right. This is what the product of a tensor product looks like. Right. So now, how would we define the tensor? How would we define? How would we describe the algebra homomorphism condition? Well, in particular, note that delta of h and times delta of g, what is that going to look like? Well, first I would have a sum that runs over all possible h's. Again, this is where the power of Sweedler notation becomes apparent, because we're not concerned with what each and every term is, which what a particular term is like. We're only concerned with the structure of the structure of the tensor product, right? So I'll describe it like this. And now the sum on the right hand would run over possibilities of g, and that would look like this. So when I multiply these together, what am I going to get? Well, one thing is clear. I'm again going to get a summation. But what is this summation going to look like? I can't say that for, again, if I don't know what these variables are, I can't say that. But that's precisely the point. These are not variables. These are structures of, these are just a representative of what the structure looks like, right? So I can just write it as H1 G1 tensor H2 G2 with the summation running over both of these, right? And the reason this is this is where the power of Sweedler notation is, right? Because H1 and H2 are not variables themselves. They're just representatives of what the tensor product looks like. So I can just write it in terms of what the structure of the tensor product is like. And this is what the structure is going to be where H and G vary, right? And now, in fact, notice that because we have this particular property of tensor products, I can rewrite this as the summation. Now, but this time it would be h times g, and the first part of this tensor, h times g, is the second part of this, right? This is exactly what we have above, but I am not, now the summation would run over h times g. And if you recall, that is exactly what the definition of delta Hg is, right? So again, we can the condition that delta is an algebra homomorphism can be written quite nicely in terms of the Sweedler notation. And there's another important thing to mention here, which is that um, this structure is behaving the bialgebra structure. It's not quite a group like structure yet. How did I get a third equality? This one. Yeah, so this equality just follows because because of this product. Again, what this these are not variables, right? This represents a particular term in the tensor product. So I can just say that, hey, you know what? I'll represent this term as a first part of h times g and the second part of h times g. So I'll, instead of running over the sum of h and g, I'll run over the sum of the product. So I'll get the first part of the product and the second part of the product. That's where the third equality follows from. So we can only do this because of the way we have defined Sweedler notation. So now notice that the structure that we have described so far is that this is not quite a group-like structure, because we don't have anything that gives us an inverse in the sense, like we don't even know exactly what we mean by inverses yet. But in what we have so far is more of like a semi-group structure, right? because there is no map that gives us the idea of what inverses are. So I can think of bialgebras as giving me more of like a somewhat an analog to semi-groups. So I would now like to have like a group like structure because groups are really good at describing symmetries. So I would like to have that, right? So how do we do that? Well, uh, the answer is that this is where Hopf algebras come in. So this is the definition of Hopf algebras. So again, it is a bialgebra. So the usual operations that we have so far, this would be a bialgebra. But along with it, I also require that there is an extra element, there is an extra map, all right? And this map is called the antipode map that goes from set H to H, such that this axiom is satisfied, which is that mu times mu composed with S cross identity composed with delta is equal to mu cross identity cross S composed with delta, and this thing is required to be equal to the composition of the unit maps, unit and co-unit map. Now, this looks like a lot to take in at first, and it feels like it's very arbitrary. But I want to, I kind of want to explain the motivation for how we come up with this axiom. All right, and but before that, I would like to make a comment, which is that in when we are dealing with groups, right, we would require that any map that gives me the inverse. So let's say that yeah, over a group, I have a map I that gives me inverse of the G, right? This is the G inverse. Then I would become an involution, wouldn't it? Because I squared would just give me identity. But this is not something that we require in this case. It is not necessary that S squared is identity. It may happen, but it's not necessary. So S is in general not an involution. That's something to keep in mind. Right. And so antipode kind of plays a role similar to inverses in groups. And why is that the case? We'll discuss that in a minute. All right. So it is possible to write down all the Hopf algebras, the properties of Hopf algebras in terms of commutative diagrams, and it is a slight pain, I would say. Not a pain per se, but it is a lot of diagrams to write, so I won't particularly go through that, but you can do it. And I think a simpler way of stating this axiom is this, right? So again, let's take a look at what this is telling us. Identity. First, we are saying that we take an element of the co-product, right? So if I apply this map to a particular element, that what is that going to give me? That's going to give me mu composed with S tensor identity composed with which acts on the sum of C1 tensor C2, right? And now I will just apply this thing. What is that going to give me? Mu applied on the summation of S of C1 tensor C2, which is going to be just the summation of S of C1 times C2. And if we do it the other way around, if we just swap the positions of identity and S here, that is going to give me the same result, right? Except that the positions of S would be swapped. And now, finally, what does this part tell me? Well, that is just telling me that uh, the unit, I'll apply the unit map to the co-product map. So the co-unit map, right? The co-unit map, what does that give me? in general, we often require the co-unit map to be just the uh, we often require the co-unit map to wait, hold on a second. Yeah, I think yeah, okay. I think I wrote this the other way around. This should be the co-unit map co-unit map composed with yeah, sorry. This should be the co-unit map composed with the unit map. Um, so yeah, I'm sorry, I wrote it the other way around. But yeah, what is this going to give me? So in general, we require the unit map to one of the easiest way to define the unit map is to just say that this is equal to lambda times something, right? Lambda times one or c times one, sorry, one times c, right? So the unit map would just become the unit of co-unit of c. So that's what we would have here. All right. So this is another way that we can express the axioms using Sweedler notation. So now, what is the motivation for this definition of the antipode map? It seems really arbitrary at first. So what I want to do first is, well, what we want is that we want to make the algebra structure and the co-algebra structure compatible, right? We have already done that in algebra, in the definition of bialgebra. We required the co-product and the co-unit map to be algebra homomorphisms, and that did it, right? But what we want is for there to be a map which gives me like an in some sense an inverse of an element, right? So let me consider the space of all possible mappings from the co-algebra to the algebra. And these are all linear maps, all right? So I know that this set is indeed a linear space, is a vector space. So what are the possible candidates for such a map? For this kind of like a, uh, I would like to define some operation on this such that it turns into an algebra, right? I would like to define some operation on this such that it becomes an algebra, right? What are the possible candidates? Well, one thing is clear, which is that function composition clearly doesn't work, right? Why does the function composition not work? Because imagine if I had two functions, f and g, both of these functions would be going from c to a, right? So f composition with g would give me a map that goes from c to a, and then it goes from a to c. But that's not okay, right? Because a and c are clearly not the same, right? So this clearly doesn't work. So I need something slightly more complicated. So um, I think perhaps the best way to define the most natural candidate for this would be something like the co-product map, right? Because function composition is clearly not working. So I'd like to define this convolution. And how do we do that? Well, think about the co-product map, right? I start off with C and I end up in C cross C. What do I do now? Well, I can now just apply F tensor G, right? And I'll end up in the space A tensor A. That's okay because F and G are functions from C to A. But now I can just apply the multiplication map and I'll end up in A again. So a function convolution of two functions that does this, right? That obeys this is something that would actually something that I actually would like. And as it turns out, this particular definition does give it an algebra structure. So in other words, this would actually be, well, okay, first I'm applying delta, right? So delta of C would be something that looks like this, right? But now I'll be applying F tensor G on this. So what would that look like? F would act on the first part and G would act on the second part. So let me just write that down. And again, of course, there is a mu acting on all of this. So that would actually give me mu of the summation of f of C1 tensor f of C2. And when I apply mu on this, I would just end up with, oh, sorry, this should be G, right? Because we're adding F tensor G. So this would just give me F of C1 times G of C2. So this is a kind of a function. This is kind of a convolution that seems pretty natural to work with. So we'll assign it. We'll give it this way. We'll define it this way, right? So F convolution with G is going to be defined like this. And as it turns out, this operation does indeed turn our vector space into an algebra. All right. And of course, the unit is just going to be the identity map. I hope that is clear, right? And actually, there is pretty easy way to check that this convolution is indeed associative. And the way we can do that is again using the Fiedler notation. So let's say I start off with FG star H and applying this to C, right? What is that going to give me? Well, that is going to give me F star G on C1 multiplied by H of C2, which is going to give me, well, it would be FC11, right? C11 just means uh, on the first one we are applying this times GC12 multiplied by HC2, right? Oops, sorry. Multiplied by HC2. Now the thing is that we know this to be associative, right? The by multiplication itself is associative. So I can just rewrite this as F of C1 multiplied by G of C21 multiplied by H of C22. And the reason I can do that is because of associativity of tensor product and multiplication, right? So when I've written it like this, I can just rewrite this again as F of C1 multiplied by G star H of C2, which is the same as F convolution with the convolution of G and H, right? So using once you know how to manipulate Fiedler notation, proving these things actually becomes quite straightforward. You just have to keep in mind that C11 are not variables. You have to understand what they are trying to represent, right? And we can actually rewrite the diagram for the commutative diagram for this associativity of these functions, right? And that's again it's easy to do, but it's slightly complicated associative diagram. But so I have commutative diagram, so I won't really write it down. And similarly, there are a couple other things that we can use. And another interesting thing is that this algebra has a right unit as well. All right. So this is a unital algebra, and the right unit is given by the composition of the co-unit of the unit map with the co-unit map. Right. Yeah. With the composition of the uh, unit map with the co-unit map. Uh, yeah. So it would actually be, in our case, the unit map is I, that would be composed with the co-unit map, right? And this is actually the right unit. And how do I know this? Well, I know this because I'll denote it as 1 star because I'm going to claim this to be the identity, right? So what is 1 star of xy going to look like? Well, I'm actually going to claim that this is an algebra homomorphism. And the reason for that is that this is going to be the same as the iota of eta of xy, right? And I know eta to be a homomorphism, so I can just write this as eta x, eta y. And now what is this going to be? So in general, our iota map is going from K to A, right? And the easiest way to define it to be write it as 1 times C or as C times 1. So I'm going to do the same thing here. So this is just going to be uh, eta of xy times 1, which I can again write as eta x times 1 times eta y times 1, which is just going to be uh, iota of eta of x times iota of eta of y, which is just going to be uh, the 1 star of x times 1 star of y, right? So not only is it a unit, the unit is also a homomorphism, right? So it's an algebra morphism. So by doing this, what we have proven is that our space actually has our space L of C comma A actually has an algebra structure. Now, uh, what I want to do is that I want to now think about a bi-algebra H. All right. Because again, all of this discussion was to try to find like a was to find a map that is acts as an inverse, right? So if I think of this as a bi-algebra and I'll denote HC as my co-algebra and HA as my algebra. All right. Now what I'm interested in is a map that acts as an inverse. So imagine if I have an identity map, right? So this identity map goes from H to H. And again, this is clearly a part of the space HC to HA, right? It's a linear map, so it's part of the space. So now what I'm going to do is define the antipode map as the map that under convolution is an inverse of the identity map. So this is my antipode map. All right. So clearly this 1 star was defined as iota composition with eta. So that's how we get one part of the axiom. And the rest of the part we just get from the definition of the convolution product. So the axiom that we have above for the antipode map just comes from this convolution product. So in other words, all we want, the antipode map, all it does is that it is the inverse of the identity map with respect to the convolution product. And it is in this sense that Hopf algebra resembles um, a group like structure because it has the idea of an inverse mapping in it. But notice that in the bi-algebra, it is not necessary for S to exist. It is totally possible for it not exist. So bi-algebra, whenever it has a antipode map, we call it a Hopf algebra. So I think that's a lot of theory, but so again, let's go back to the example that we discussed before, right? The example that we had discussed was this group algebra, and we already saw that it is a bi-algebra. Right? The fact that both of these are algebra homomorphisms is quite easy to verify. So can I give it a Hopf algebra structure? The answer is actually yes. You very much can. And how do you do that? Well, what you do is that again we define S of G. This is the antipode map to be G inverse. So now in this case, this is very much the case that S squared equals identity. In this case, it is possible, but it is not always the case. And the reason it works here is because our Hopf algebra is commutative. And the commutative Hopf algebra, it can be shown that this relation holds. But in general, Hopf algebra need not be commutative. So it does not, it is not necessary that this relation holds. All right. And I think now it's kind of, in this example, it's kind of clear how the antipode mapping is acting as an inverse, right? So let's check the antipode axiom just so we know for sure that this is indeed this is indeed a Hopf algebra. So how do we do that? Well, let's just write down what the antipode axiom was as cross identity, cross sorry, not cross composition with delta, right? So when I apply a particular element, say G to this, again, we are going to be using these definitions here, right? What is that going to give me? Well, that is just going to be mu composed uh, mu of S cross identity of G tensor G, right? Because of the way we define the coproduct now, which is then going to give me mu times G inverse tensor G, because again, S will act on this and identity will act on this. And the mu would just multiply these two together, because remember, mu acts on A tensor A, right? So it would just multiply these two together, and that would give me G inverse times G, which is just one in the group, I mean, right? The identity in the group. So I don't want you to confuse it with the identity in the field. So I'll just I think I'll instead write this as E. Right? And you can do similar computation with the identity and S swapped. That would again give the same result. So the only thing that needs to be verified is whether the co-unit axiom gives us the co-unit and the unit obey the property, right? So all we want is for unit composition of the co-unit to be equal to this thing over here, right? And is that the case? Well, co-unit just gives me one, doesn't it? Right? The co-unit just gives me one. So what I mean is that uh, the co-unit of any number is just going to be any element G is just going to be one. And since my unit map is again a co-algebra homomorphism, I can prove that the image of one is just going to be the identity in the G, right? So here G instead of this we would have KG. So it's just going to be the identity in G, and therefore we again get E. So we can see that these two are in fact equal. So we have verified the antipode axiom, and we've seen that this can be given a Hopf algebra structure, right? And there are other examples of Hopf algebras as well. So I think one of the very standard example is that if you consider the SL2 Lie algebra, then that is actually a Hopf algebra, right? And that is actually a quite an important example also. Then another example that you might have seen, another familiar structure would be the tensor algebra. The tensor algebra also is an example of a Hopf algebra. Um, yeah, so a lot of the structures that we are familiar with, that we have seen in our classes, perhaps uh, do actually form Hopf algebra. So I'll give an example of the SL2 Lie algebra, right? So SL2 Lie algebra is generated by these three elements, where H is equal to 0, 1, 0, 0, Y is equal to 0, 0, 1, 0, and X is equal to 1, 0, 0, minus 1. And we also have commutator relations on this. So H comma X is equal to 2X, H comma Y is equal to minus 2Y, and X comma Y is equal to H, right? So this is the standard multiplication map, which is why it's a Lie algebra, right? Because there's a bracket on this. And in fact, you can give it a Hopf algebra structure by considering what we call the universal enveloping of a Lie algebra. Right. So I won't go into the details of what a universal enveloping is, but essentially it is a way to construct construct an algebra structure on top of a particular existing Lie algebra. And in fact, it can be proven that every universal enveloping algebra is always a Hopf algebra. The universal enveloping algebra actually plays an important role in representation theory of Lie algebras as well. So yeah, it is quite cool. So yeah, I think so yeah, I think this is like kind of a good place to stop, because so I think I have like the point here is that all these objects that we've described right now, they are just the basics of what quantum groups are. We still haven't reached the definition of a quantum group. So quantum groups are just basically Hopf algebras. They're a particular type of Hopf algebras which we call quasi-triangular Hopf algebras. All right. uh, yeah, quasi-triangular Hopf algebras. So these are just a specific type of Hopf algebras, and um, yeah, I think we can maybe introduce that next time when we talk about some other things as well. But there are some other structures that are related to quantum groups that are actually really important. So an example of this is what we call the R matrix and the Yang-Baxter equation. R matrix and the Yang-Baxter equation. And these are particularly important because these actually pop up a lot in physics. And in fact, it is possible to, they're very intimately related to quantum groups. And it is actually possible to define or construct certain space times using this solutions of the Yang-Baxter equation, which are called the R matrices. And that is the like kind of the fun application of quantum groups uh, because they pop up a lot in like all of these places. So yeah, I think this is kind of a good place to stop. We have already covered a lot of stuff, so I hope this wasn't way too much. So yeah, if you guys have any questions, I'll able to answer now. Sorry if the talk was too long, but thank you for attending my monologue. Does anyone have any questions? Okay, if not, then we can stop here or stop the recording. Thank you for attending, guys.